Hello, my name is Khalil Stell, and I am the developer, creator, and maintainer of SJSU-Dev2, and right now I'm going to show you the contributors video, or the contributors training in this video. So I'd go over some things we're going to be going over in this video. It'll be a refresher on object-oriented programming concepts. We'll be going over the object-oriented architecture of SJSU-Dev2. We'll be going into unit testing, the pre-submit checks and continuous integration, design documents, and finally the Git workflow for contributing to the project. So first we're going to start off on object-oriented design and object-oriented design concepts. So we're going to go over a couple of keywords. These ones should be pretty general. I'm just going to go over these as a little refresher. The first one is class. A class is a collection of related data and functions. An object would be a single instance of this class, kind of like creating your own type of variable. Methods are functions within that class, and when I say implements, what I'm saying is that it's a class that implements an interface if it inherits it. We'll be going more into interfaces in the following slides. Okay, so an interface. In C++, an interface is a contract that specifies the set of methods a class implementing the interface must provide. And actually, this particular word interface is common across many other languages. Java, you can potentially do the same thing in JavaScript, and so on and so forth. A lot of type-strong languages have interfaces. But to give it a little bit of a easier to understand definition, in other words, in C++, a class that inherits an interface is forced to implement the set of class functions that the interface does not implement itself. So I have a bit of a demonstration here. I'm going to click on this link here. I'm bringing up Godbolt, also known as Compiler Explorer. I absolutely love this thing and highly recommend everyone else use it. Here we have an example where we have some type of stopwatch interface. And here we have what's called a virtual function or virtual method, and it's been set to a pure virtual, which means setting it equal to 0. That means that it's not actually defined. Because it's not defined, you actually cannot create such an object. The attempt to instantiate this object would actually give you a compiler error. For example, if I come over here and I try to type in stopwatch interface, there should be a compiler error popping up here saying cannot declare variable interface to be of abstract type stopwatch interface. What that just means is that this particular class, as we would call it, an abstract class, which is another word for an interface, this abstract class cannot be defined or cannot be constructed on its own. It's not a real object. It is an abstract object. Its methods only exist to enforce that other classes that inherit it provide these same functions. So if I comment this out, and then I comment out this method here, what you'll see is that a similar thing. We have the stopwatch implementation down here that implements this interface, and this interface requires that you create an increment method with the same prototype, returning a void, which we do have here. And it also implements some get counter that's const that also returns int, which was defined here. When I attempt to instantiate this, I'll get an error saying that cannot declare variable stopwatch to be of type abstract class or abstract type stopwatch implementation, because the following virtual functions are pure within stopwatch implementation. This particular method does not currently exist inside of stopwatch implementation. The only way to get rid of this error and the way to proceed is to implement it. So it's a way to force other classes to follow a certain structure, a common structure for how their classes should be designed. This can be very useful and very powerful, because not only does it force the user to use these particular methods, but it even goes even further. It has way more capabilities than just this. Interfaces are also called abstract classes. I kind of said that already. An abstract class abstract classes are abstract. Opposite are real, therefore they cannot be constructed into a real object. Now the big part here is polymorphism. This is actually a key point of SJSU-Dev2 and is what enables its ability to be used across many other platforms, many other microcontrollers. So polymorphism is the condition of occurring in several different forms. This is a dictionary definition. When it comes more to the CS definition, it is the ability for an implementation of an interface to act as the interface type, yet have its own implementation. So before I'm going to break this down a bit into keywords. First keyword is virtual, which you guys saw before. This enables polymorphism for a class and its descendants. And another thing that we need to have is that, or we need to know, is the fact that pointers can point to parent classes. This is the ability in C++ and in a lot of other languages that you're able to pass a child off as if it were the parent class. So if you had some class like the stopwatch implementation that had additional methods, if you passed it to a class that's looking for its parent, you could call the parent set of functions on that class, or you could, and it gives you that ability to do so. Now, with these two things, with the ability to have a pointer of the parent class point to a child class, and having the virtual keyword, this allows you to pass an implementation of an interface to a function or class. And here's a demonstration here. So here we have the stopwatch again, but we have a second, milliseconds, and microseconds example. So we basically took the same stopwatch from before that has increment and get count. And we made a class for seconds, milliseconds, and microseconds. And this might be a bit of a weird example. It doesn't really make too much sense, but for the most part, think that this is going to increment every second. This is going to increment kind of every second too, every time you do an increment on it, but it's just by thousands of it. And this one's a million because there's a million microseconds in a second. And here we have something that uses the interface, use interface. And it will run the increment 3 times, and it will get the count whenever you ask it. What we can do here is, because we are not taking specifically microseconds or specifically milliseconds, we're taking the stopwatch interface. That means that we can now pass any one of these objects to this class, and it can call upon its methods, that specific implementation's methods. So we actually see here that I am now using use interface for use seconds. I can call the use interface 3 times, same thing with milliseconds, same thing with microseconds. And I can get count for each one of them. And you'll see that we'll have 3, 3,000, and 3 million. Even though the class hasn't really changed, the use interface didn't really change in its code. The code's pretty generic here. But because I can change how each one of their increments operates, given the fact that each one of them implements the increment differently, I can use it to my advantage, and I can pass that same timer of sorts, the same stopwatch, to any one of these different classes that uses the stopwatch and get different results from either one of them. As it becomes super handy when it comes to the core what SJDev2 is, which is building device drivers that are modular and that also work across different microcontrollers. So now going into the architecture, I think this will really, now we've gone over some of the few concepts here and there, it's really time to go into a lot of the architecture of how things properly work. First thing I'm going to show is the legend. It kind of goes over the pieces of, or kind of like the way things are shaped. So in this area here, we will see the parent class and some child implementation. We have this solid arrow. The solid arrow is an indication of inheritance. Whereas over here we have polymorphism. And the dotted arrow represents you passing an implementation or passing some object to some class through its constructor, typically. And here, anything that's connected to some class at the bottom here means that this class contains a local variable, a local, typically reference to this implementation's parent class. That's why it's usually denoted as red. So this particular class has an interface reference, and it sets it using the implementation passed to it through its constructor. So keep that in mind. Composition classes take implementations through their constructor and save it to their own internal local reference of an interface. And here we have just inheritance that shows that this parent class, this parent interface, is enforcing its interface onto this implementation class. Do note that for things inside SJDev2, you can have multiple interfaces to child implementations. It really depends on what you're building. So first off, we're going to go over L1 peripheral composition. So here we have namespace SJSU, we have some GPIO, we have some things that it can do. For example, you should be able to set the direction of a pin. You should also be able to set its level, either high or low. And here we have an implementation that's specific to the LPC40XX. It implements the SJSU GPIO, and it then creates its own version of direction and set level. One thing I'm kind of missing here is that I should have override, but it kind of was going a little too far out here, so make it a little longer, so I kind of omitted that. But for the most part, you can see that it's basically forced to implement these, otherwise you'll get a compiler error. The neat thing about this is that it doesn't have to just be for the LPC40XX. And if you didn't know that, that's the chip that's used on the SJ2, which is used at SJ San Jose State's Computer Engineering Department. We also can have it implemented for STM32. We also have it implemented for the TI chip, which is the MSP43OG2, which is used on the TI Launchpad. I don't remember which one exactly, but each one of these implements this interface. As long as each one of these implements this interface and can generate a GPIO, any other class that requires a GPIO can just simply take the interface as its local variable, and you can pass any one of these depending on which one you're building for. So if you're using STM32, pass in the STM32 version. If you're using LPC, pass in the LPC version, so on and so forth. The next one is going to be level 2, which is the HAL abstraction, so the hardware abstraction layer. And this is how you kind of compose things for the hardware abstraction. So here, we're actually going to need a GPIO, but we have a button class. This button class, like I said before, takes the interface of GPIO as a reference and assigns it to its own internal reference. Then when it does detect release, let's say it like checks to see if the pin is high, checks if the pin is low, whatever it may need to do. The idea here is that it doesn't need to worry about the specifics of the implementation. It just needs to know that if it calls the read pin, that it'll return back a high or low state. All it needs to know is that if it tries to set a pin to an input, that it'll do the job of doing it for that particular platform. So as long as GPIO does exactly what it's stated to do, button will always operate properly. We have a little example project or program where we create such a LPC GPIO, and then we pass it over to a button, delay a second, and then we go and ask if the button has detected a release. This can be done in so many different ways, but for the most part, this is a very basic example. And then this diagram just shows that we have some hardware abstraction, in this case button, that contains a GPIO interface as a local variable, and then we pass in GPIO implementation. Now here's another composition. This one is really just kind of showing the fact that, let's say we have more than just one way to build a button. Yeah, most of the time buttons are pretty simple, but let's say you don't need to just take a GPIO. Let's say you can take I2C. Let's say you have some type of random device. I'm going to call it BTN 3194. Now, this chip does not actually exist. It's not a real thing, but let's say there was an IC that you just connect up tactile buttons to, and every time you press a button, it can detect if it was a rising edge or a falling edge, or if it was pressed or if it was released, and then all you do is talk to it over the I2C serial communication and then get information from it. That means it could very easily just operate as a button class. So if that ever happens, when we realize that we have two things that basically do the same thing, and they seem so similar that they could literally be underneath the same interface, well, we should make a new interface. So here I made this new button interface. I don't really show it here. You can obviously expect that it has a detected release. But it's here as a way to say this hardware abstraction, this GPIO button or button 3194 must abide by button, such that if anyone else needs a button for their code, well, they have it. Then all you have to do here is pass in GPIO implementation. And, oops. All you do now is pass in some implementation of GPIO, and it should do the thing. This would be specifically for the GPIO button example. If this was the BTN 3194, then you'd have to pass in an I2C object. This one would change to I2C, this one would change to I2C, and this one would still be inheriting the button interface. Now, L3 composition, usually it's pretty much synonymous with the L2 composition. They're really just pretty much the same. The only real difference with this one is that usually you're composing a lot more stuff. So in this case, we have some remote controller. This is some type of IR emitter. So think about the one that you would use for your TV. Well, if we had such a button or such a remote controller, we would probably need a GPIO for power faults, something that we could use to measure if a pin that tells us that the AA batteries are low, it could pull the line low, and then we realize, oh yes, we need to, that means we're having a power fault. We could have a button for volume up, a button for volume down, and an IR emitter. Now, this is very simple, but I didn't want to write so much that it would take up the entirety of this page. But you can kind of get the idea. You can continue this on. And in here, we'd have references to each one of those different objects, and the implementation of the remote controller would be down here. Here we can kind of see what's happening. We have some type of volume up button, which implements button interface. We have some GPIO power fault GPIO that implements the GPIO interface. We have some of a button GPIO, so we don't know which pin the user is going to need or what care to use for GPIO, so we just make it open, so they can just make their own GPIO, pass the GPIO over to volume up, and then volume up now has the GPIO can control. Same thing here though. We saw this infrared control, which also could be used through a GPIO, and we pass that implementation to the infrared emitter, and then we enforce the infrared emitter through this interface. Let's say we have a variety of different types of infrared emitters that use different methods and different interesting means of controlling these infrared emitters. Maybe we have one that doesn't require us to pull the line high and low on our own. We just simply send it a byte and it sends that information over the air or through its emitter. We don't really know, but if it seems like this can be generic, we can turn this into its own interface and work it from there. Below here, we now have a remote controller, and it has a set of local variables, one GPIO interface for the power fault, one infrared emitter interface used for emitting the data over to the TV of sorts. Then we have a button interface, and I kind of have this thing looking like an array. The idea is that you have multiple button interfaces, each for each button that you'd like to take care of in order to build up your remote controller. And that is pretty much the composition and architecture of SJDev2. The main idea is that you should be able to compose and take if you're working on the STM32, if you want your code to work, let's say it's a remote control, but you want to switch microcontrollers, this code here can very easily swap over. All you need to do is, rather than using the LPC version of the GPIO, you'd use the STM32. Rather than use the TI version of the GPIO for a button, you use the STM32. Same thing with this one. And then that stacks into this, which then stacks into this. And now automatically, all you need to do is swap out 3 implementations, 3 names, and you're good. You could actually, we have a method in our documentation on how you design this such that none of the drivers from the other code leak into your application, so the binary stays as small as possible. It's aside the scope of this particular presentation, but the thing I just want to bring up is the fact that things in L2, once you add another L1 and L0, you add another platform to the mix, it automatically has full control in order to do what it needs to do. It can just work. So you can very easily, you no longer have to be afraid of staying with the same chip. You can move chips however you like, as long as it has the appropriate implementations for its L1 layer. Okay, so we went over kind of how things work in SJDev2 and kind of the architecture there. But one of the other big things about the development environment, the development platform, is that the majority of the code should be unit tested. And if you're going to be contributing to this project, your code will need to be unit tested as well. Now, there are a lot of different ways that you can go about testing your code in SJDev2, or just in firmware in general. But there are a couple of ways that we do in SJDev2 that we believe are sufficient enough to be able to really be able to do some of the following things we're going to talk about. So first, I'm going to go over some fundamentals, and then we'll also go into why we do unit testing. So what is unit testing? Unit testing is a system of testing where the smallest testable parts of an application, i.e. a function or a class, are individually and independently scrutinized for proper operation by comparing the actual output of the function to the expected output. An example would be a function that calculates the area of a circle. So we have some calculate the area of a circle, returns a float, takes in a float as a radius. And if you know what the equation is for the area of a circle, you might notice that this is incorrect. You see 2 times 3.4 times radius, which I think is the circumference. When in reality it should be pi r squared. So radius times 3.14. In the above example, if tested, we would see that something is critically wrong. If we call the function with the input parameter of 3, we get the actual output of 18.04, that's what it returns to us, when we expected 28.26, which is the correct answer. So why did we test? Why was it important that I went over that? Well, one thing it'll do is it'll detect mistakes in your code. Maybe you really meant to actually write the function for circumference, and you were also writing the one for area, but you somehow mixed them up and you put one in the other. Well, I mean, all the code looks right, and if you were just doing a glancing look, you might not have noticed. But if you write code that's supposed to look for that, you're more likely to detect these mistakes. And honestly, one last thing I'll put into this is the fact that you are more likely to find mistakes if you have to write code twice that requires both to be either correct or very wrong in a very particular way to both be a false positive. For example, you can think of these cases. The case where your code is wrong and your code is right, and a case of when your test is wrong and your test is right. If your test is correct, as in you wrote your test correctly, and your code is correct, therefore your code is written correctly, then you should pass your tests. If your code is incorrect but your test is correct, your test should fail. Your test will detect that it failed. If your code is correct but your test also is not correct, it should also fail. And if they're both wrong, they should also fail. There's only really one case where the thing seems to give you a false positive, and it's only in the cases where the test is wrong, and it just so happens that the output of the test and the output of the code equal each other, but in the wrong way. One tip, if you notice that your code passes the first iteration over, the first time you run it, break it afterwards just to make sure it can fail. Moving forward, another reason why we test is to reduce the time of debugging. No need to reflash to test. If you just have to make the test code, you can run it on your computer, run through the tests. No need to flash and take so long when you're doing it on your host machine. It acts as another form of documentation. If we go and edit someone else's code, and their test fails, you have to think about this. When we edit that code, do we mean to edit that code? Do we mean to change its behavior, or do we just want to go in there and refactor it somehow? If it changes its behavior, and that was undesired, we now know that we can now look at that test code and see, okay, how is this thing supposed to operate on the hardware, or how is it supposed to operate in general? The test can act as either a list of instructions that gets the hardware in the right mode, or it acts as a check for the logic of a particular hardware abstraction or L3 application side software. And we can learn from that by just reading their tests. Another useful thing about tests is that it detects if a change breaks the code base in some way. If I change or refactor some code and it breaks the test, I now know that the functionality of the code has been changed, even though the only change that was supposed to happen was a more cosmetic style change or more cosmetic refactoring or even optimization to the code. At the minimum, it should stay functionally the same. And if this happens, that means that we have somehow broken that piece of code. Another thing, though, is that depending on how you may have changed some other functions or classes, if their methods are actually completely used, and you have changed some part of how the implementation of those classes is being used, and it somehow breaks this particular test, even though they're not the same thing, they're not the same exact unit, then we can detect breaks in that way. Again, after that, it forces us to build code that's easier to verify in tests. This part's really important. Not all tests are equal. And you'll hear that line come up again. Not all tests are equal, or not all code's equal. Not all code's easy to test. You can't just merely just test any code. If you have some code that is 1 million lines long, it's in a single function, and has 127 different conditionals, and they're nested, and there's a lot of other things that are in there, trying to write a test that goes through every single one of those branches is going to be insane. The better alternative would be to write smaller functions, small functions that do little pieces of what that bigger function was trying to do, test those individual parts, and then verify that each one of those individual parts works. If the parts all work individually, and the way that those parts are used the way that those parts are being used within the class that uses them, or that function that uses them, as long as that's correct as well, then it should come that everything should work properly. Should. Sometimes there are weird behaviors or side effects of particular classes or to particular functions or pieces of code that may go beyond simply that little bit of logic, but generally that's the case. Another thing that it does is it gives us confidence about our own code. As a little example, I used to write code for a satellite back when I was working at NASA. It was fun, it was great. It was just the fact that I was terrified of the fact that I was writing some code that would take information from a sensor that would be able to tell you its radial velocity, what orientation is relative to the Earth, where the sun is, where the moon is. It needs to know all these different parameters in order to be able to adequately work out in space. And I was afraid that, if I made a small little mistake, I shifted over some of the bit stream of information that I got from the sensors about that by just one bit, that would completely destroy and throw out all the data. And we would probably jettison ourselves right back into the Earth or maybe even to the ISS, something terrible. But because of the fact that I tested my code and I verified over many different edge cases that the code operated as intended, and I even took some sample data that they had acquired in order to make sure that came out properly. After I did that, I felt pretty confident in the fact that my code would work. Do we know if my code works? Is my code up in space right now? No, the satellite blew up in the rocket on its way up. But I assure you, though, that it probably would have been working just fine once it got up into space. Rest in peace. The next step is gives developers using our code confidence that our code works. It's not just enough for us to feel confidence in our own code. That's fine. That's good. It's good to feel good about things. But really, the really important part is that anyone else who uses our code has confidence that it actually works. They can look at our tests and see that, okay, they're testing these things, they're testing these edge cases, and they can determine whether or not they think that our platform is a useful platform for them to be able to develop, especially if they find that we have a testing framework built in for them to use, as well as they know that our code's being tested all the time. Now, why do we design with testing in mind? That was one of the other things that we brought up. Well, not all units are easy to test. I kind of explained this before, but it gets a little difficult when you do write testable-ish code, but there's some parts in it that might make it a little difficult. For example, a lot of times when you're writing for embedded systems, you're given some address literal as defined within a macro, and you're going to use that in order to manipulate some registers. So we have to come up with some way to be able to manipulate those registers, but also be able to test them later so that when we're running it on our host machine or on a server, that we're not pointing to arbitrary addresses that don't make any sense on our host machine, but make valid sense on the microcontroller. You come up with some way to test setup for harder registers. And here I'm just saying that we need to see what the function actually sets the structure's value to. So if you have a structure that you point to, we need to make sure that the information, the data in those registers are being changed appropriately. The other one is testing functions that call other functions. We need to be able to see what is exactly put into those internal functions in order to verify that those functions operations fit against expected. And then also the above two cases are a good reason why why it has to be understood and planned out before we do any coding, before any code is really written. If you don't end up writing your code in such a way that is testable, in some way that you can swap things in and out, then you'll end up stuck where your code is tightly coupled and there's really no way to be able to test that part without testing other units. And if you remember from the beginning, we said that unit testing is testing each unit independently and on its own. So all code must be planned and designed with the idea of testing in mind. And there should be no added class methods that are only used for testing. That should have two style guide. This is just stating that the way that you write your code shouldn't require that we inject other additional code just for the purpose of testing, like friends and such like that. It should be testable by default. So I'm going to go over some fundamental general terms. One of them is called dummy. Usually a dummy is a structure or value, some type of data that is used only for like testing and only contains data for testing data. So for example, let's say you are setting up a timer to a frequency of 1 million. Well, you throw in a dummy value of 1 million or 1 megahertz. A unit, the class that's under a class or test that's being tested, or just a function or something that we're testing in particular, some smallest unit of a particular class. A class, really isn't itself its own unit. It's its methods and how the different methods interact with each other that really becomes the units. Expected, whenever we say expected, we are trying to say that the values that you expect a function to return or create. The actual is the values that we actually get from a function or a method as a result of it being run. Now, general terms, we have stubs. Stubs are objects that return predefined values that, when called during a test, it is used when we cannot or do not want to involve objects that would answer with real data or have undesirable side effects. So the idea here is that if we had some function, let's say we had some function and it will return to you the results from a database. It returns to you some data from a database. Well, it might take some time to do that to a database. Or if we're running like, a million servers and each one of them trying to also access the database, we can end up DDoSing the database. Basically, we just want it, we know what we want. We just want a particular structured set of data, and we'll let the rest handle the rest. If we're doing something like for let's say, a HTTP request using a Wi-Fi module on one of our boards, and it takes some time, why not just fake that HTML return or that TCP or IP, like that particular returned binary, return that information immediately so that we don't have to wait this entire time. We know that if we get valid data, that we'll be able to operate on it. So why not just go with that? Stub that thing out, return a predefined value, and do not involve real data. Because then that means that if you're not connected to the internet, your host test will break. And that should not be the case. You should not be you shouldn't be forced to depend on these other external factors. Next one is fakes. Fakes are objects that have working implementations, but are not the same as the production one. Usually they take some shortcut and have some simplified version of production code. For example, if I am trying to do something with, let's say I know that if I run some set of functions, that it changes the state of some hardware that I'm working with, and that whenever I ask for information, it will change over time. What I could do is I could have the fake act as if it were that piece of hardware, or act as if it was giving you a certain sequence of data that you're expecting, and then work that way. So it's similar to a stub, except in this case it's not returning just a single predefined value. This one actually has some intelligence there that can handle acting in place of the object you would normally send in. And finally, mocks. Mocks are objects that register calls they receive. In a test assertion, we can check if a mocks method has been called and verify that it matches the expected actions. Just to be a little clear, a test assertion is basically testing, is a line of code that will check your actual versus your expected. So in this case, what we can do is we can mock methods of a class and check to see if that particular class's method has been called appropriately. And then this is a link to where we found these definitions. We did try to come up with our own, but we wanted to take them from some place that we thought was a little more legitimate than our own experiences with this. All right, so now I'm going to start going over the frameworks that we utilize in order to do testing. So this is a little bit of explanation of why we even have this here. Unit testing frameworks are used to handle the tedious tasks of unit testing, so all you have to worry about is your unit under test and testing its functionality. No worrying about how do we manage, making so many different tests, how we manage, making sure we run all of them, all the algorithms for that, how do we handle, doing all this polymorphic, making mocks like that. No, this stuff handles everything for you. So the first one we use is Catch2. Catch2 is a unit testing environment to verify, automate, and run unit tests. Fake it can generate mock objects from interfaces. And finally, we have FFF, which can generate and define mocked functions that can act as fakes or stubs. So FFF stands for Fake Function Framework. It's really handy when you're trying to create something that will need a function pointer passed to it, and then you can also stub it, and you can not stub it. You can also, you could stub it. You can also mock it, and you can also fake it. Okay, so we're going to start off with the framework Catch2. Catch2 is for creating unit tests. This means that you can define unit tests. You can verify. It gives you verification macros to check expected output against its actual output. And it shows a set of passing and failing checks and tests. So here we have some file with a multiply method or function in it, and here we have it returns an int. It takes two ints and multiplies them together. In the test below, we have a test case, which actually itself is incorrect. Here we defined a test case, test mult, and then we have given it the brackets represents the test set that it's a part of. So if you have a bunch of other test cases with the name brackets multiply, it'll whenever you try to execute the test with that argument multiply in those brackets, it'll run those set of tests. The more of this information is actually found inside the catch2 documentation is not too important here. But the thing to understand is the fact that you can create these tests. You can also then create these checks that will then check the expected output, the actual output versus the expected. In this case, 1 times 1 should be 1. In this case, 2 times 2 should be 4, but we made a little mistake in our when we were writing this test, and it came out 5. This should fail. Then we can go in, figure out, oh, that's incorrect, put a 4 here, and it's correct. Or if we found that this is actually supposed to be, this is 4, and this is supposed to be something else, then we can go in here and make sure that this is correct. And here's a little example of running this test and seeing, here's some other things, like some other factorials that were tested. We have our multiplication test, and that 4 is not equal to 5. This failed. And we have a couple failed tests here. Fakeit is another framework, and it can generate custom objects based off of a class interface. Interface is inserted through the technique of dependency injection with polymorphism, dynamically reassign virtual methods, and it can record calls of history of what function/stub was called, and record argument history for each faked function. It can also assign a sequence of values to a stub's return value. So you can, in a sense, like create a chain of stubs where it iterates through each one of those chains. You can do a lot more than I think what we're just specifying here. You can look into its documentation, but here's a little quick example. We have some interface. It has a foo and a bar method, and we make a mock, pass it in the interface object. Then we say when the method called from mock called foo, whenever it is called, return a 1. Here we can make a interface reference, get the object reference from this particular mock object. Then when we run i.foo, it will print out 1. Here we have verify method, and this is actually an assertion that can check to see if that method was called. And here we have a verify method that checks to make sure that it was specifically called with only 1. It was only called once. Or I'm sorry, that it was called being passed a 1 is what I meant to say. And if all these are correct, and in this case it would be correct, then you would pass this test. FFF can generate mock functions that can act as fakes or stubs. You can record call history of when each fake or stub was called, record argument history for each fake function, and assign a sequence of values for a stub to return. Similar to Fakeit, except this one's specifically for functions. Here we have this chip. It's a display that takes a chip select and a SPI transfer function, and here we're basically just passing these objects or these functions into this area here. Then we can check to see if this structure gets generated. When you do this, it generates a structure called SPI transfer underscore fake, and then it has a table within it called arguments, argument 0 history, and checks to see, after every single call, on call 0, does this equal SPI display memory mode? On the second call of this, here you see if k display memory mode clear was used. And that happens right after the clear screen. So we expect that after we construct this object and we do clear screen, that these two will have been passed into the SPI transfer function. So the limits. Fakeit cannot actually replace or spy or operate with non-virtual methods. So if your method is not virtual, then it's not going to be usable. That's kind of the reason why, So we're kind of limited to that. So that actually influences some of the style guides. Like for example, for how-tos that don't have interfaces, you actually just make their methods virtual. And what ends up happening is when you run the compiler at a higher optimization level, it should devirtualize those calls and no longer have to do a virtual call for it. FFF cannot replace global functions. It would be great if it could, but it cannot. It cannot overwrite them. There are some hacks and ways to kind of make that happen. But honestly, the best thing right now would be that, a global function should be easy enough to test on its own such that it won't cause any issues or weird side effects. And if there's something that is a function that would cause some side effects, it shouldn't be something that is passed, that is just global. It should be passed into another object. So you could create your own version of that, your own dummy or fake version of that, stub, mock, or fake version of this, and then pass that into your class. Attempting to do this so will result in linker errors, and the number of arguments that can be checked is limited. So here's some techniques. This is the important part. The techniques utilized in SJDev2 are test by side effect. This is specifically for L1 peripherals. It can be used in other layers potentially, but it's because everything you do inside of L1 is almost always a side effect. It's always a side effect. It's always altering something outside of just like your local variables within your objects and such. It's always altering some global state. We have to do some type of test by side effect, and we have an example of how to do that. In this case, what we do is perform our testing. We pass an address to a local memory location in place of the absolute memory location that the L1 code has. So besides having a absolute address that we use, we actually store that inside of a pointer, and then we relocate that pointer to point somewhere else. Then we can run all our algorithms on that. There's some example here that I can go over. Number 2 is dependency injection through polymorphism. So pass an object reference / pointer of an object to your class for use during the test. So if your class needs a GPIO and you want to do some tests with that, well, you can pass in. You can make a mock of the GPIO interface and then pass that in as its version of GPIO. Then you can inspect all the different calls. And finally, dependency injection with function pointers. This can be used for L3, newlib, and utility. Basically, you pass in a function pointer of a function that your class will use, or some object or function or whatever we'll use. And then finally, there is replace global function pointer. So if we ever do have a global function that needs to be called in multiple different locations, the alternative in SJDev2 is actually to make them into function pointers. They syntactically will end up being called the same way that a typical function would be called. They wouldn't look any different, but you could reassign them, so the label can be reassigned. And that means that we can reassign them during a test if it makes it easier. Like, for example, the standard in and standard out functions are function pointers, and they can be swapped out. So here we have a couple examples. I'm going to open these up. Oopsie-daisy. All right, let's do that again. So here we have DAC. And if you look at DAC, what we've done here, zoom in on that a little bit. You'll see that we have this LPC DAC type def. This is a pointer to the registers that make up the LPC DAC peripheral. And rather than using this absolute address that we're given here to do all our register manipulation, we set it equal to our DAC register pointer. Then we just utilize the DAC register pointer throughout all of our code. Now, this method is not as sophisticated, and because there's only one DAC, it's fine, but for this particular platform. But there are better ways to go about this going forward, and the other things like I2C, SPI, and UART utilize this thing called predefined structures. You can pass those in as objects into your constructor as well. Yeah. So this is our point of injection. Notice this guy is public, and he's also not const. So I can actually modify this inside my test. If you go over to the test, you can see that what we've done is, you ignore this for now, but you can see that we've created our own version of the LPC DAC type def. We're creating our own version of like this structure that represents the DAC's hardware. We clear it out, and then we set the DAC's single static register to the pointer of, or to the address of the local DAC port. So then when we call things like initialize and such, what we can do, like here for like write DAC, we can actually check to see if after we run test subject, and that's the object that we've created, it's DAC test subject here, we can actually check and see that when we run the write command, that this mask 0, which is defined here, is equal to the local port.cr, because this particular class is going to manipulate that pointer. If it manipulates that pointer, that means it's manipulating this object here, or manipulating the structure here, and we can read off each one of the individual fields, each one of the different variables within that object, and then we can check to see if they equal the appropriate information. And then here's just a definition where you can find the LPC DAC, and it has 3 uint32 registers, 32-bit unsigned register bits, registers, and yeah. So that's pretty much this. Next one we're going to look at is buzzer. Now there was actually an example of this, of the L2 and L3 driver testing using FakeIt in DAC, but I just kind of wanted to mull over that so we can go into the buzzer. Buzzer needs a PWM in order to operate. So what we do is we make this mock of the PWM object. We're already inside the SJSU namespace. And what we do is we fake the method initialize, set duty cycle, and set frequency. We grab a reference. Then we pass that PWM reference in here. We can actually probably just take this, put it smack dab in there, but it doesn't really matter. Now what we can do is when we run initialize, the buzzer should initialize the PWM and set it to a particular frequency. In this case, we default to setting it to 500 hertz. The duty cycle should be set to this volume divided by 2, which is basically this here. And the idea here is that the duty cycle for a buzzer cannot be any greater than 50%, because otherwise it doesn't end up doing much. So whatever our volume is from 0 to 1 would be half the duty cycle, be half a percentage of the duty cycle. So this is divided by 2. But it should default to 0, so it's not on. Lastly, you should do set frequency, which is set the frequency to the appropriate frequency of 500. And then you can continue on to use these for everything else. So you can do beep, and you can check to see that the set frequency was set to this, and that the frequency was set to that. Or sorry, set volume was set to this, or set duty cycle was set to this particular volume, divided by 2. And that the set frequency was set to this, and set to the appropriate frequency. And this goes on until we've basically gone through all the checks to basically make sure that buzzer uses the PWM appropriately. If this PWM works appropriately for the platform we're on, and the logic for our buzzer does operate as expected, then it will work. Finally, we have testing a pure C++ code. And this one's pretty simple, pretty down the line. Here we have some function that if you give it some value, you give it the low bound, the upper bound, and then the new lower and upper bound, it will map this value to the new range. That's pretty much all it does. So in this case, 75 is basically 75% through from 0 to 100, and negative 10 to 10 it ends up being 5, and so on and so forth. So you basically just call the functions, no function additional calls, nothing special here. It's just math here. You get a result that returns it back. You check to make sure that the results in this fit each other. Okay, so that was pretty much it for unit testing. And if you ever need any help when it comes to unit testing, go into the code base and look at the other tests, and it can give you a pretty good idea. There's still some cleanup that needs to be done on some of the tests, as you can see there. Like, for example, there's some things that didn't need to be called in a certain way, or some things that could have been a little cleaner. But for the most part, a lot of the example code, a lot of the other tests act as a really great example code of what you can do and what other people have come up with in order to test their code. Next, we'll be going into continuous integration. And so if you don't know this, continuous integration is automated code evaluation. Continuous integration is a development practice that requires developers to integrate code into a shared repository several times a day. Each check-in is then verified by an automated build, allowing teams to detect problems early. In SJSU-Dev2, this means that we have some code that is created that will make sure to go through your code to make sure that it fits our standards. By integrating regularly, you can detect errors quickly and locate them more easily. So So now I'm going to go over some of the things that we check. So the first thing is that we have this thing called pre-submit SH, which is basically a means of submitting. It's a thing you should do before your code actually gets through to the code base. First thing we do is we do a build test. We test all the demos and all the core code to make sure each one of those builds appropriately. Next thing we do is we do code linting. We make sure to statically check your code to make sure that it follows the Google standards, making sure that no lines go above 80 characters, make sure there's a new line at the bottom, make sure your the includes that you have are in alphabetical order, all those things. We also check your variable names to make sure that they fit the SJSU-Dev2 standard. We also do unit testing. So what we'll do is we'll compile and run all the library tests and make sure that anything that you introduced did not break the current tests or any of your tests that you introduced. And this can be executed on your local machine by going into any one of the projects and just running make pre-submit. It'll go through the entire sequence. Now, next thing is automated code evaluation. We have Travis CI. Travis CI is our hosted continuous integration service used to build and test software projects hosted on GitHub. It's great and it's open source. It's free for open source projects and it'll be tested at no charge via Travis CI. What it does is it first clones the repo, then it runs setup, then it executes make pre-submit, then it checks, then it creates code coverage files and submits them to coveralls. Then it generates code documentation, and then that can be found at that link there. One thing to also bring up is that Travis CI doesn't just do this on Linux, it also does this on Mac. So we make sure that we check that the setup works on either one, and that the code doesn't somehow break or do something weird on Mac than doing it on Linux. Those little small little nuances are quite uncommon, but they do happen, and when they happen, they're kind of annoying because they're kind of difficult to kind of figure out. So here we have a sample pull request. Couple items here, and I think if I go to show all, you can see a continuous integration. We see coveralls, and we see Codacity, which we'll go into a little bit. And here we can see that we built for Linux. We also built for Mac. If we scroll through here, you'll see that it went through the setup process, which is quite large. Goes for days. And then we also ran through setup, building all the projects, linting, checking doing a tidy and checking all the files for variable name validation. Then we also built all the test code, made sure to run it, and made sure that everything was clean at the end. And it looks like everything looks good here. You may commit. And then we also have coveralls, which basically just an example and kind of just shows us how much coverage we have. We used to be a lot higher, but now we're at 70% when I started figuring out that there's some parts that weren't getting through, that coveralls wasn't detecting as part of our code. So that's pretty much it. The last one that's not actually even listed here is Codacity. And basically all it does, I'm not logged in. But the base idea is that what it'll do is it'll give you alerts if your code does not fit certain standards. It goes beyond the things that we test, and it can test you're using sprintf. That's hazardous. That can cause problems. You should use snprintf, which you can give a length of how long it can go before it overflows the buffer, stuff like that. Okay, we're getting towards the end. We have the design documentation. Here we have design documentation. It's a high-level overview of your design along with an API and a rationale on how you will approach the implementation, software testing, and manual testing. It's really just there as a way to communicate to me and other people who are on the team what exactly you're trying to do, just to do kind of a sanity check to make sure that everything's all on the up and up. But it's also useful for people in the future to be able to understand why you had a certain approach and what you were doing it for, and just kind of be able to understand a design. The design doc template is here. We have an example. I'm going to skip the example for now, but we're just going to go into this design doc here. Here we have an SJSU, San Jose State University Compi Internship Summer 2018 design doc template, which is still invalid. It's still valid, so you can still use that one. This one looks like it is, Put an objective, a few sentences to talk about the objective, to put in some background, rental information, previous versions, stuff like that. Detailed design, detail of what you're designing and how. Caveats, really anything about the section is caveats to your design and what you're deciding to do. How are you going to test it? Are you going to fake? Are you going to mock? Are you going to do polymorphism injection or dependency injection through polymorphism, dependency injection through function pointer, pass dummies, dummy data, or are you going to do a test by side effect, something like that? Usually when we're designing these design docs, you need to specify one of these. Integration testing, describe how you will go about doing integration testing. So how you're going to test with the actual SJ2 board. And then finally, a demonstration, some type of demonstration to like a demonstration project, as well as like, how you're going to demonstrate this and the capabilities of your library. Okay, so the final section here is Git workflow. Now we use Git here, and so everything's on GitHub. I'm not going to go into too much of the details here, but for the most part, the SJDev2 follows the following open source Git contribution model. You fork SJDev2, you make your feature branch, you implement a change in your feature branch, create a pull request. This is where you go up for review, and I get to check out your code, and I get to see what's there, or I or anyone else who's a contributor. Then we go through the code review and iteration. Then we do pull request. Then the pull request, if it's good, if it's been approved, and it gets through all continuous integration, pull request is merged into the repo by contributors. There's this awesome link here. It's fantastic. This whole presentation will be on the description. But this actually goes through all the details about how to go about doing this. So I'm not going to go into that too much. I'm just going to go over some of the things that are more about standards of SJDev2. For example, this kind of shows a picture of what I was talking about before. The other link kind of has that too, so I'm going to skip over this. Here, for Git commit messages, the first line should be a title, should not exceed 50 characters. New line after title, so make sure you have a little gap here. Then the following paragraph contains detailed summary here. Do not include something that is obvious in the explanation just from looking at the actual commit. And the line length cannot exceed 80 characters. Every commit must end with a reference to an issue number. So if you don't have an issue number somewhere in here, then I will probably tell you to add one. Workflow makes sense. What makes up a commit? Each commit should be a self-contained packet of working code. No commit shall break continuous integration and get submitted. Each commit should just basically do one thing. Meaning you cannot have a commit that makes two separate and disjoint changes. A commit that changes the ADC and then PWM, but those changes have nothing to do with each other. Like, oh, I'm going to clean up ADC and PWM, but like you didn't need to do those separately. Or you're doing something like I'm going to fix up something on ADC, I'm also going to clean up PWM. That's not acceptable. Put those into separate commits so that if we ever need to roll one of them back, it's very easy to pick away that one and then put the other one in place in the history. Next, each commit should have an associated issue attached to it. So the bottom line should have, if it resolves the issue, but resolves hashtag the number that represents that issue. If it is not resolved, then just put an issue hashtag, just so it links that particular issue, and we can see a PR or a pull request that came in that was supposed to contribute to getting that thing resolved. Now, another workflow thing is making a pull request. It's also explained inside the previous that link that I showed before. But if you have completed your work, you may create a pull request. There's a little button usually up here on the it's getting in the way. But at the bottom here, pause for a sec. Yeah, so a little button down here at the bottom, pull request, and you can do that. Each pull request should only be one commit in length. It can be multiple commits, but for the most part, you should stick to just one commit in length. If you have to make edits to that particular commit, you should amend that commit and then force push that back up. And that's pretty much it. Yeah, so that's pretty much the entirety of the SJSU contributors document. There's still more documentation to read and more things to learn about SJDev2, but I hope that everything that you learned here gives you enough information to get started and for you to begin contributing to the project and hopefully putting these things, getting some experience in developing on this project and making some really awesome stuff. Thank you again for listening and for helping out with this project. Bye.